Good afternoon, Professor.
Good afternoon, Caroline.
Good afternoon, Professor.
Good afternoon. Wait, that was so fast. I feel like that was Savannah again, but that went so fast. Was that? I don't know.
Yeah, it was.
It was. All right, thank you. Nice to see you again. All right. And now the chat. I don't know why okay. Good afternoon, Stephen. Good afternoon, Caitlin. Good afternoon, Kevin. Good afternoon, Amanda. Good afternoon, Irene. Good afternoon, Adon. Good afternoon, Estrella. Good afternoon, Erica. Okay, and I think that and Rashman. Good afternoon. If I didn't say, okay, all right. Ooh, getting comfortable there. Okay. Thank you for indulging me last week. I apologize for that again. Travel has been a little bit challenged lately with weather and I don't know which is more challenging, the weather or people anticipating the weather and then making decisions. But anyway, I apologize, but thank you for understanding and indulging. So here we are. So I'm going to get straight to business. And hello, Yuben. And hello, Jose. 1 second. Oh, and I just lost my board again. Hold on. Okay. Here we go. Okay. So, as is often the case, the top equation on the board right here is in principle where we left. Oh, good afternoon, Jose. All right. Good afternoon. The top equation is in principle where we left off last time. I'm going to reestablish it. Right now, I'm going to remind you sort of what it means, where it came from last time. It came from the middle of homework 2. And what we're going to try to get to, where we are going to get to by the end of today, is the bottom equation. That's the whole point of today, to get from the top equation to the bottom equation, in effect. One thing just to remind you, I mean, there are subtle differences between those two equations, subtle but super important. Well, some more important than others. One difference I just want to remind you again, there's no distinction ultimately between X naught or A, a capital A. Like sometimes we use X naught when we want to emphasize that it is the value of X when T equals 0. We want to emphasize that it's the first displacement from equilibrium. And we use A when we want to emphasize that it is the maximum displacement from equilibrium, or in other words, the amplitude. But they both ultimately are interchangeable. X naught and A, and they're both measured in whatever units X is measured in. Okay, so what's the deal with the top equation is where we left off last time. Well, I'm just switching the view. Oh, and there goes the board again. Okay. Yes. Here comes the set. Okay. Where we were last time, last Monday, we were going over homework 2. We were in part 1. We were at question G. And question G asked, is X equals A cosine omega T plus 3.5 a solution to D2X dt squared equals negative omega squared X, right? Which is a mathematical question. It's saying, does this particular example of a function, of an xt function, solve this particular differential equation, right? Which is an equation that tells you about a certain xt derivative. In English, what we're really being asked, or in physics terms, what we're really being asked there is, does X equals A cosine omega T plus 3.5, does that describe a harmonic oscillator, right? That's like the larger topic that we're in right now is harmonic oscillation. And what we believe is that if a system can be described by that differential equation, that specific differential equation, or a differential equation of that form, then it is a harmonic oscillator. And one way to describe a harmonic oscillator that we've thus far established is X equals A cosine omega t. Like we've been saying, oh, X equals A cosine omega t, or X equals X naught cosine omega t describes the position function for a harmonic oscillator. It, for any given t that you plug in as the independent variable, it spits out X position as as a dependent variable, right? So that's what we've been saying. I'm just putting the board back up again. Person in the other class, in one of the other sections, who was watching these videos, pointed out that more time is spent on these videos just trying to get the board back than physics, and that's probably true. Good afternoon. Yes, no problem. Thank you. Good afternoon. Awesome. Okay, here comes the board again. So what I'm saying is, up until now, our big equation that was the position function for a harmonic oscillator was X equals A cosine omega t. That solved the differential equation d2x dt squared equals negative omega squared x. What we found in question G of part 1 of homework 2, what we found is that we could throw in this term 3.5 into the end of the parentheses. We could throw in this term 3.5, and even when we took two derivatives of that new X expression, even with the 3.5 inserted in the parentheses, if we took two derivatives of that X expression, we still found out that the second derivative did yield back the original X expression times omega squared times -1. I.e., the chain rule took omega out of the parentheses, just like it always has, but it didn't take the 3.5 out of the parentheses. So in other words, the 3.5 did not adversely affect the derivatives. We could stick it in there, and both of our derivatives still worked out the way they needed to solve this differential equation. So what we inferred is that you could stick a number like 3.5 in there, and it still seems to be a solution. Therefore, physics-wise, physically, even with that 3.5 in there, we still have a harmonic oscillator. So apparently a harmonic oscillator can be described in slightly more complicated or slightly more general terms than we thought. We thought a way to describe a harmonic oscillator was X equals A cosine omega t plus 0. And now we're saying, oh, you know what? It doesn't have to be plus 0. It could be plus or minus anything. It didn't, 0 was just a special case of any number that could be stuck in there. So, okay, again, I'm just we took the two derivatives on Monday. We saw this. This is all being inspired by question G. Again, I hope you understand, like, one of the reasons these homeworks take us so long to go through and why you have so much time to do them is that the homeworks are not just exercises. They're not just reviewing and practicing old skills. Each next question is trying to set us up to advance the topic further. So this question tried to show us, oh, you can stick an extra number in the cosine argument and you still have a harmonic oscillator. So, and by extra number, I mean, it could be any number, positive or negative. It could be plus or minus, so to speak. We could even do this. Oops, sorry. As long as that number, as long as that number is a unchanging number, a constant, and as long as it's measured in radians. So from now on, we're going to use a Greek symbol, the lowercase letter phi or phi, to designate that extra number that can be in there. And we're going to call that phi or phi the phase constant. Okay, so from now on, I'm saying, and I hope this is clear. Oh, and there goes my board again, even though I'm drawing on it. I still agree with Doug that it should be about active time on the thing. But anyway, hold on. Okay, if you look at the top equation that's about to beam in, if you look at the top, I'm saying that top equation is our new, more general way of describing a harmonic oscillator. As of a week ago, we were saying, well, hopefully you're getting used to that top equation, but as of a week ago, it was plus or minus 0. But now we're saying it could be any number, and we're calling that any number phi. Okay, that's what we concluded last week. But now, so what? What is, well, not so what, but that's the math. The math shows that you could stick an extra number in and it doesn't change the math. But what does it physically mean? What is this extra bit, this thing that we're now going to, from now on, call the phase constant? What does it actually physically represent for an oscillator? Okay, so what this page says is it represents a head start or a delay in the phase of the oscillator. What do I mean by phase? I mean the place, that word says place. I mean where it is in the cycle. And when I say cycle, like, again, we're always picturing a mass going back and forth on a spring as the most representative or vivid example of oscillators in general, harmonic oscillators in general. And anything that's a harmonic oscillator is something that can be described by that differential equation and can therefore be pictured as acting just like a mass on a spring. Even, for example, even if it's the temperature system being discussed in homework 3, the whole point of that homework 3 is to show that even something as sort of immaterial or abstract as temperature, if temperature can be described by that differential equation, then that means temperature is fluctuating up, is oscillating up and down with a constant frequency in all of the manners and details and behaviors of the way a mass changes its position up and down, back and forth harmonically. Anyway, so phase is where you are in the cycle. That phase constant phi designates where you are in the cycle when the whole thing began. If the phase constant is 0, as it has been for the last few weeks, if the phase constant is 0, that means the cyclical motion began at the beginning of a cycle. Well, duh. I mean, what does that mean? It means that we started our stopwatch when the system was at an amplitude position. Remember in homework 1, the mass was on the spring. When it had velocity 0, and when we started our stopwatch, time equaled 0, when the mass was all the way out at 15 centimeters from equilibrium and with a velocity of nothing, right? The experiment began when the mass was being held at 15 centimeters from equilibrium. It was being held there. So we started our stopwatch, we let the mass go, and it started going back and forth like this, back and forth like this. Because it had 0 speed at 15 centimeters, that means it had no kinetic energy. That meant all of its energy was potential. That meant that was the most energy it was ever going to have, right? Energy is conserved. So the farthest it would ever get on either side ever again from that moment on was 15 centimeters. Because that's the place where all of its energy was potential, and it can't get any more energy than that. So we started timing that system when the system was at its maximum displacement from equilibrium, its end point, its turning point, its 0 kinetic energy point, right? And the math just said x equals a cosine omega t. Like plus nothing. Plus nothing means that we started the whole situation at the farthest point from equilibrium. If, for example, so I'm going to show you the math now, what phase constant means. If we give a phase constant of pi over 2 radians, for example, remember, phase constant always has to be measured in radians. It's some number that goes in the parentheses that we're going to add to omega t, that we're going to take a cosine of. So it's got to be measured in radians. So let's say the phase constant is not 0. let's say we do like x equals a cosine omega t plus or minus pi over 2 radians. What would that mean? Well, pi over 2 radians is a quarter cycle, right? Where did I get what? Where did I get that? But please always remember the key that brings this all together, always that links all the cosinusoidal mathematics to the oscillatory physics. The key is knowing that there's 2 pi radians to a cycle. I mean, to a circle, but therefore to a cycle. There's 2 pi radians in a cycle. A cycle is 2 pi radians. Therefore, pi over 2 radians is a quarter of a cycle. Now, I'm just using pi over 2 as an example here, but it's a nice example because a full cycle, 2 pi radians, always means just that, a full cycle, i.e. a round trip, i.e. there and back, right? So 2 pi radians means going from positive amplitude, say like positive 15 centimeters, all the way through the equilibrium, all the way to the other side to negative 15 centimeters, right? And then all the way back. That's a full cycle. That's 2 pi radians. Therefore, pi radians would be to go all the way there, but not to come back. Would be to go to a negative amplitude position, right? And pi over 2 radians, a quarter of a cycle, would mean to go just halfway there, i.e. to the center, to equilibrium, to x equals 0, right? So in English, a phase constant of pi over 2 radians means we didn't start our stopwatch when the whole cycle began. We didn't start our stopwatch timing, we didn't start timing when the cycle was at when the mass was at amplitude position. We waited until the mass had already done a quarter of a cycle. We waited until the mass was at equilibrium, and then we started our stopwatch, right? That's what it means, that t equals 0 was declared when the thing was already a quarter of its way into the cycle, right? Let me again. Phi equals 0 means starting our stopwatch at amplitude. Phi equals pi over 2, for example, would mean starting our stopwatch at equilibrium. I just said in English, let me show you the math. I'm saying, just plugging in, like assume that phi, so again, phi is that Greek letter that stands for the phase constant. If phi equals 0, and we're assuming here an oscillator, so x equals a cosine omega t. Oh wait, don't look at that. Don't look at the blue thing up for the. I mean, that's for later. All right, so if phi equals, so if phi equals 0, we're saying then x equals omega t plus 0, right? So what does that mean? That means at t equals 0, if you in your head plug in 0 for t, right? Plug in 0 for t, then 0 times omega is 0. 0 plus 0 is 0. So you would get at t equals 0, you would get x equals a cosine of 0. I'm going to switch the page for a second. I'm going to ask you a question in a second. I'll put that page back in a minute, but I want to ask you a question. So be prepared for a second. It won't be a hard question, but it'll be a question. So far, I'm saying if phi equals 0, then when t equals 0, I believe x equals a cosine of 0, right? Like that's what you just wrote down. X equals a cosine of 0. Now, first of all, please tell me in the direct chat. I will put the page back. If you haven't written everything down yet, I will put the page back, but please tell me in the direct chat, what is the cosine? And I'm going to wait in the direct chat, in the private chat. First of all, what is the cosine of 0? In the direct chat, what's the cosine of 0? Oh, that was fast. Oh, that was fast. Oh, that was really fast. That's 3 people. Wow, that might have been record time. 3 people just went in the chat. If you're one of those 3 people, I'm talking to you. And all 3 people had the same answer. And it was the right answer. I should stop right now. That's a hat trick. That's awesome. Yes, and the right answer. And congratulations to you 3. There are 4 people. Oh, because I didn't say the answer yet. Oh, that's awesome. Oh, that's 4 people that just got the right answer. And I didn't say the answer yet. So anybody that put it in now is still totally, wow, that's awesome. I want to congratulate those 4 people for getting the correct. Wait, so I'm going to take it a step further. Should I take it a step? Oh, no, okay, I will in a minute. I'm not going to push my luck. Oh, was that 5 people? Wait a minute. Oh my God. Wait, 1, 2, 3, 4, 5, 6, 7. I love this class. You're totally with me. 7 people just put in direct chat and all got the same answer and it was right. And you might think, well, if you're one of those 7, you might think it was an easy question, but I guarantee you it's not. I mean, it just shows that you know something, and it really shows that you're paying attention too, which is even more delightful. So yes, what 7 people just said, and you should all submit for points, please, for participation points. 7 people just said that the cosine of 0 is 1, and I agree with them. The cosine of 0 is 1, which, and I will turn the page back in a minute, but I'll go a little further. Oh, that's fine. By the way, I'm sorry, so an 8th person just had the honesty to admit they used a calculator. That's fine. First of all, I appreciate the honesty, but that's cool. You're still paying total attention. And yes, I mean, I can eventually show you tricks maybe, or help you eventually not have to use a calculator, but that's totally legal. I mean, that it would be legal that as long as you know what you're doing on the calculator, it's fine. Yes, the cosine of 0 is 1. And just one way to remember it is just always, I think it's easy to remember that sine of 0 is 0. That's what I always remember. Sine of 0 is 0. It sounds like you're a snake, or ecans, as they say in Pokemon, because it's snake backwards, yeah. And then cobra is cobra backward. Anyway, Arbok, like ecans evolves into Arbok, which means snake evolves into cobra. Anyway, whatever. Yeah, if you say sine of 0 is 0, I think that's easy to remember just because it's like a bunch of S's, and it's true. Sine of 0 is 0, and therefore cosine has to be the other one, which is 1, whatever. But yes, cosine of 0 is 1. So that means in this context, if, and I will turn the page back in a minute, but if phi is 0, then at t equals 0, x equals a cosine of 0, which means a times 1, and a times 1 is a, right? So far what I'm saying, I'm just showing mathematically, and I will turn the page back in a minute so you can see it and copy it down or whatever. But I'm saying when when phi equals 0, that means that at t equals 0, x was a, that we started timing when the mass was at the amplitude position. That's what phi is 0 means, that we started timing in the most natural, convenient, obvious place. We started timing when the mass had come all the way out here and had run out of speed in one direction and had yet to start going back in the other direction. So it was in its slowest motion. It was going 0 meters per second. So it was the easiest sort of to catch with a stopwatch. I think it's the easiest place to start your stopwatch when you see that mass at amplitude. That's when that setting is phi equals 0. Now, if phi equals pi over 2 radians, then we plug x equals a cosine omega t. I'll show you on the page, but I want to see if anybody can figure this out on their own first. If phi equals pi over 2, then at t equals 0, here, actually, yeah, okay, here we go. Then, but, where it says but in the middle of the page, right here. But if phi equals pi over 2 radians, right, then x equals a cosine omega t plus pi over 2, right? Like not plus 0, but now plus pi over 2. Now we're sticking in a pi over 2 term into that parenthesis. So now it means when you started the stopwatch, something else was going on. When you started the stopwatch, when t was 0, you still plug in 0 for t, and omega times 0 is still 0. So you're doing x equals a cosine 0, but now plus pi over 2. So now you're doing the cosine not of 0, but of pi over 2. And what is, I'm going to ask now, and be careful with this question. I want to ask in the direct chat, I'm going to ask, what is the cosine of pi over 2 radians, right? Just tell me that. You don't have to tell me anything about x or anything like that yet. But what is the cosine in the direct chat, please, of That was fast. That was very good. That was two people. Oh, two people very fast and very agreed with each other and very correct. That's awesome. That's three people very correct. That's awesome. I'm not saying the answer yet. I love this game. It makes me feel so alive. We have three people in the direct chat with, maybe it's even more. Oh, it is more. 1, 2, 3, 4 people in the direct chat with correct answers. I'm going to wait for one more just to make myself happy, but that's awesome. I'm asking, yes, great. And by the way, thank you for showing. Oh, I can't say it. Okay. Yes, that's 6 people in the direct chat. 5, yeah, 5 people in the direct chat, and all of them agree and all correct. That's awesome. They say the cosine of oh, wait a minute. Yeah. Sorry. Yeah, they say the cosine of pi over 2 radians is 0. And I totally agree. Now that you could do on a calculator too. I do want to make a plug for, if you're getting used to this, if you really start understanding that 2 pi is all the way around, so pi over 2 is a quarter of the way around, we're really talking about this angle, a right angle, what you might call a 90-degree angle. We're really talking about what's the x coordinate of a right angle on the unit circle. And the right on the unit circle, well, I'm backwards, but on the unit circle, if you go to the top of the unit circle, because you're opening up all angles from the positive x-axis. If you go to the top, your y coordinate is 1, but your x coordinate is 0. The cosine of pi over 2 is 0, which means, okay, my last question. Then when t equals 0, if phi is pi over 2, when t equals 0, if phi is pi over 2, then what is x? Let me say that again. And I think someone just answered, but when phi is pi over 2 radians, then at t equals 0, what is x? And close, but oh no, correct. I'm sorry. Totally correct. I'm sorry. Totally correct. My bad. Everybody who's in the direct chat is totally correct. And that was fast. Yes, it's right. Because x equals a times 0, and a times 0 is 0. That's awesome. You guys are totally with me. And you're actually a little bit more with me than the other class was. What? Did I say that? I did not say that. What? But to make it absolute. So we're just, hopefully you get, so that just sort of mathematically showed what the purpose or what the meaning of phi is. Phi is a setting that basically said, yes, it is also 0. Very good, people. You guys are rocking my world. So the upshot of this is phi tells you how far away in the cycle you started from the amplitude position when t is equal to 0. If phi is 0, then you started at the amplitude position when t was 0. If phi is something else, if it's like a quarter of a cycle, then you were a quarter of a cycle away from the amplitude position when the clock started. If phi were pi, then that means you started on the other side when the stopwatch started, right? So it's where you are in the cycle when the clock starts. That's what phi is. And I think you guys get it. That's really good. And you can ask questions in the chat if you want, but everybody who's been participating, which is a lot of you, seem right on top of this, and that's great. So we're almost ready to move on. I'm just looking at the time. All right. So now let me just emphasize one thing. There was a confusion in the other class. No one's expressed that the following confusion yet. I don't want to create a confusion that doesn't exist, but just to be absolutely explicit, everything I'm talking about right now in lecture, everything we've been talking about in lecture and recitation is the mathematics of one harmonic oscillator. This is a oscillator. This is any system in the world that behaves like, can be pictured as a mass going back and forth on a spring. Everything we're talking about here, we can picture as the relationship of some variable, such as position, to time, to the variable time. So any of our functions and any of our graphs, we're picturing that time is the independent variable. And in this case of a mass on a spring, like horizontal position is the dependent variable. And we're saying that anything that can be described by this differential equation will manifest all of the details that are manifested by a mass on a spring. So for example, it could be a bob on a pendulum string going back and forth in an arc. So instead of X standing for position on a meter stick, we might say theta stands for angular position, like somewhere on an arc, or like as in homework 3, X, instead of X, it could be like D standing for temperature. And then we're saying that temperature is depending on time, but we're always having one dependent variable being spat out as the output of the one input that is time. We're talking about one system, one object going back and forth in this fashion. This is a harmonic oscillator. In lab, you've already been working with something else that's more complicated than this. And this something else is what I want to start transitioning to like right now. Just to be clear, I guess, I mean, not to give away the farm or spoiler alert or anything, but in lab, you're already, distracting, hold on. Sorry. Okay, in lab, you're already up to something called waves. I want to get there in a moment now in lecture, but I need to be very clear. Like, we haven't said anything about waves yet in lecture, and nothing of what I'm talking about here is waves. What I'm talking about here is harmonic oscillation. I'm talking about the amplitude, the frequency, the period, the phase of one harmonic oscillator. That's what I'm talking about here. Now, how do I get to the material that you've been dealing with in the labs? This is how. So I'm now about to finally transition this to what you've been doing in labs. Oh, and let me say one more thing, though. What you've been dealing with here, this is a thingy thing, a particle. We've had to develop all this abstract mathematics because the mathematics are advanced. But all the mathematics that we've been doing describe one distinguishable material, countable, identifiable, massive material particle that's moving through space and time in a measurable, observable, predictable way. The mass on the spring, no matter how many times it goes back and forth, or no matter how interesting its motion is, it is a mass that we can look at and point to, say, there's a mass that's here, and then it's 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 here. We have, so far, everything we've been talking about has been the particle or particular motion of a harmonically oscillating object, a thing. Now, oh, right, and here's the summary of everything we've been saying so far, right? I mean, I think you get. So what we're now saying is that a object or a system oscillating harmonically in time can be described by this equation. One oscillator can be described by this equation, where A or X naught means the amplitude measured in whatever units X is measured in. Omega is angular frequency. It's radians per second. It's the number of, it's like omega is right. Omega is the cycling rate of cycling per time. It's measured in radians per second, but as long as you always remember that a radian is a sixth of a cycle, right? Or 2 pi radians make up a cycle, then omega is the rate at which your cycle, it's how many cycles you're doing per time. And phi is where you start in a cycle. Like All right. So everything we've been talking about can be summarized by this one equation, and it is one oscillator. The question is, why did we even introduce phi? Like, why do we even have to bother with a head start or a delay? Like, if all the laws of physics are the same in all inertial reference frames, if physics is the same in all coordinate systems, that means we can choose whatever coordinate system we want to describe an experiment. And we generally would choose the coordinate system that's most convenient for us. So in other words, what I'm getting at is, why do we ever bother with a phase constant that isn't zero? Why would we ever start our stopwatch at some place other than the most convenient, easy place to start it? And the most convenient, easy place to start it is when the oscillator has stopped moving temporarily. The answer is that we would. If we only had one oscillator, we would always set phi equal to 0. And that's why we didn't even know about phi until last week. We could do all of this computation and stuff, assuming there was no phase constant, because we choose to start our stopwatch at the most convenient place. But the one time, or the one situation where we need to track a head start or a delay with regard to cycle is when we have more than one oscillator, right? And they have more than one oscillator that don't start in the same place at the same time. Then when you have more than one oscillator, you still will say that where one of them is starting, you'll still start one of them in the most convenient place possible, but if they're both starting at two different places, you can't do the same for both of them. So phi becomes important when we have multiple oscillators. And what I want to do now is look, and the whole reason, honestly, that we've been studying one oscillator so much and so deeply to make sure we can master what's going on with one oscillator is, what we really are interested in is what happens when we take a whole bunch of oscillators and put them together in a particular way. What we're going to do now is we're going to consider now the simplest, meaningful way that we could arrange a whole bunch of oscillators and have them acting as a collection. And it's this. Okay. So what we're going to do is we're going to consider the simplest meaningful collection of identical harmonic oscillators. Now, what do I mean by simplest meaningful? Well, let me start with here's a really simple collection we could consider. Someone's here. Obviously, I'm going to draw this and do equations in the next slides, in the next 3 slides. But let me give you background on what I want to start imagining a whole bunch of oscillators, a whole bunch of them. I want to imagine, I want to keep things as simple as I can, but I want to start thinking what happens when you have a group of oscillators doing something interesting. So I want it to be interesting and meaningful, but I want it to be as manageable as possible. So let's start with the idea that all the oscillators are identical, meaning they're all masses on springs, and they're all the same springs of same stiffness K, and they're all the same mass M, right? And so if they all have the same Ks and the same Ms, we're going to be able to assume they all oscillate at the same angular frequency of omega, right? And let's also assume that they all have the same amplitude, A or X naught. So we have a bunch of oscillators that are all going to be identical. Let's say that I'm going to allow them to oscillate along a vertical axis like you did in your initial labs in lab 1 and in lab 1. Assume that all the oscillators are going to have vertical oscillations. But let's all assemble them along a horizontal axis. So again, I'm going to draw a picture in a second, but I want you to start picturing with me that I lay out a meter stick on a table, and I put the first vertical oscillator at the edge of the meter stick at the 0 position. Then I take the next oscillator and put it at like 1 centimeter. Then I put the next vertical oscillator and put it at like 2 centimeter mark, and then the 3 centimeter mark. So I'm distributing vertical oscillators uniformly along a horizontal axis, right? That's the situation here. I want to make a group of oscillators and have them all do something at the same time in a large space. Well, so they're identical oscillators. So again, it's about as easy as you can picture. Once I say group of oscillators, picture all the easiest factors you can, and probably that's what I'm picturing. One thing though, if I put out all these vertical identical oscillators and stretched them out all evenly spaced along an x-axis, if I then also gave them all the same phase constant, if I gave them all the same phi, so that they all start at the same place at the same time, and they all go up and get to the same place at the same time, and then they all go down, and then they go up and go down. If they were that identical, if I made it that simple, that's too simple, because that's too simple for there to be anything to study. What I mean by that is if I put a whole bunch of oscillators stretched out on an x-axis and have them all oscillating vertically all together perfectly like that, like that'd be fun, maybe that'd be nice to watch. But if they literally all did the same thing together, then there's no meaningful sense in which it's a multiplicity of oscillators. Like then everything I could say about the motion, I might as well just picture one really wide spring just going up and down and up and down, right? Like there's no distinction being played out between oscillator number 7 and oscillator number 8 if all of them are doing the exact same thing. So I want to go one touch more complicated than that. I want to take advantage of the fact that I have a bunch of oscillators. I want to actually like use them as a multiplicity. So let's say what I'm going to do is everything that I just said with one modification. I'm going to take all these all these identical vertical oscillators. I'm going to distribute them uniformly along an x-axis. I'm going to give them all the same amplitude. I'm going to assume they have the same angular frequency because they have the same stiffness and the same mass. But I'm going to stagger them in phase. I'm going to stagger them in phase, which makes things a little more complicated. Like in other words, when the first one starts, the next one's not going to start. It's going to get a little delay. It's like, or when the first one I'm going to start the first one and I'm going to wait a little bit before I start the next one. And then I'm going to wait a little bit before I start the next one. Or if you want to put it the other way, I'm going to arrange them all into different places in the cycle and then let them all go from different places in the cycle. Same point, right? But I'm not going to have them all go at the same rate, but I'm going to give each one a little stagger compared to the last one. That will make things just a little bit more complicated and more interesting to watch. But that's good enough. To do that is already enough of a complexity that I'm not going to make it any more complex than that. So I'm going to say, yes, let's stagger them in phase. But as you see here at the bottom, it says in brown, let's stagger them in phase by a constant step. A constant step. So in other words, if I let the first one go and I wait a half a cycle for the next one, let's say, so I let the first one go and I wait until it gets to equilibrium position, and then I let the next one go. Well, then let's follow that rule from then on in. Let's say we wait for that one to get to equilibrium, and then we let the next one go. And then we wait for that. So I would stagger them each by, let's say, for example, pi over 2 radians, right? That's what I want to picture. I'm going to draw this on well, it's going to be drawn on the next slide and with equations and stuff. But what I want you to picture is a horizontal collection of identical vertical oscillators, but all of the oscillators being staggered in phase by a constant step, like a constant number of radians for each meter that I let my eye travel along the x-axis. So it would be something like this, right? Like it would be like it's a little bit of a crowded drawing, but like, right? I mean, this is what I'm talking about. So we've got these vertical oscillators set up, and each one has some position. It's at some position, y, called y. I mean, each one is at some height at any given moment in time, called y. But each one is placed at a horizontal position called x. So I place the very first oscillator, I'm actually going to call the 0th oscillator, because I place it at the edge of the meter stick at x equals 0. So, right? And then the very next oscillator, I place at x equals 1 centimeter, let's say. And the very next oscillator I place at x equals 2 centimeters. But as the drawing is trying to indicate, let's assume that like the very first one starts at below the starts at y equals y naught. And then by the time it gets to equilibrium, then the next one starts. And by the time that gets to equilibrium, the next one starts, etc. Right? So if we're staggering them all by, for example, then this is an example. This is an example in which the stagger amount in phase is, in this case, it's pi over 2 radians for every meter, for every next oscillator. So for every next centimeter along the x-axis, right? So if I were to write down a separate equation for each, so I have this whole bunch of oscillators now. Each oscillator has its own equation. All the equations are going to be the same amplitude, A, and the same angular frequency, omega, but they all have a different phase constant, right? Like the first, so this is where phase constant becomes important. So the first one has a phase constant of 0. It was at the amplitude position when I started the stopwatch. So it's the oscillator that's at the 0th mark on the x-axis and it has a phase constant of 0. But that's this one. But let me see if I can close. Hold on a second. I know I'm like being a ghost. Hold on one second. Did that help? That did not help. One more second. Hello. Wow, that really didn't help. Wait, where am I? Hello. Wait, that's really weird. Wait, oh, okay. Well, I don't know why. I don't know what to do. All right. Well, anyway, what I'm trying to say is if you look at the oscillator that's at position X, I don't know why this is happening. Okay. If you look at the oscillator that's at X equals 1, it has a phase constant of 1 times pi over 2, right? Like but then the next one, not coincidentally, has a phase constant of phi equals 2 times pi over 2. And then the next one at X equals 3 has a phase constant of 3 pi over 2, right? For each next X unit that we look, we're increasing the phase by that constant amount, right? So the equations have a pattern to them. If I wanted to capture all these equations as one, and there goes my board. Okay, if we wanted to capture all the equations in one equation, we could because of that pattern, right? We could, in this example, where the step in phase is pi over 2 radians per every meter that we go, we could capture the whole thing and say, okay, no matter which oscillator you want to look at, we could write y equals a cosine omega t plus pi over 2 times x, right? Like, so if you're looking at the 0th oscillator at the x equals 0th position, you plug in 0 for x and you would get y equals a cosine omega t. If you're looking at the 7th oscillator, which is at the x equals 7 meters position, if you want to know the equation that describes it, you would plug in 7 for x and say, okay, y equals a cosine omega t plus 7 pi over 2, right? I mean, so we can capture this whole ensemble with one equation. But now, note, I want to go one step. So I'm trying to put this all together as a package. If I go one step further, I realize like pi over 2 is just the example that I'm discussing right here. Oh, that's so funny. I just was saying that. Wait, someone just put in the direct chat exactly what. Wait, that's a great question, direct chat person. What I'm saying is pi over 2 is just an arbitrary example that I'm using right now, just because it's easiest to picture. I'm using pi over 2 as an example, because it's the same example we used like 20 minutes ago. Pi over 2, so great question. The person who in the direct chat just said, why are we saying pi over 2? Let me make clear to everybody. It's just an example. I'm going to broaden in a moment to all examples. But what the example means, pi over 2 means a quarter of a cycle. So I'm using it because I think it's sort of easier to picture than a lot of other numbers I could use. I could use any number as the phase step. But if I use pi over 2, what I'm asking you to picture is that when the first mass is at amplitude, when we start our stopwatch, we start this whole thing going. The first one is at amplitude, and we start it. But the next one, we don't start moving until the first one is up to the equilibrium position. We wait until the first one is a quarter of a cycle in before we set the second one in motion. A quarter of a cycle, because that's what pi over 2 means, quarter of a cycle. So when the first one is up to equilibrium, the next one is at amplitude. Then when the next one goes up to equilibrium and the first one is up to negative amplitude, then the next one starts at amplitude. Like we're just staggering them by half. If I use the example pi over 2, I'm saying that each one of these oscillators is staggered by a quarter cycle. When one is at the amplitude, then the next one is at equilibrium, and the next one is at negative amplitude, and then the next one is like back to equilibrium, but like a cycle later. We just keep waiting a quarter cycle before we start the next one. Or we set them all up, we place them all in this shape, and then let them go. But I don't know, wait, but direct chat person, does that answer? So what I'm saying to everybody is right now, I'm just imagining that pi over 2 is just an example. And if it were the example, I think the picture would look something like this. Like while some of the masses were right at equilibrium, some would be as low as possible, and others would be as high as possible. But that's just an example. But the important thing of the example is that they're all at different places. That each one is at a different place in its cycle from its neighbor. I don't direct chat person. I don't know. Tell me if that made sense or not. I don't know. But no, they're all going up and down. They're all going up and down. They're not just going down. I don't know if that, maybe tell me in the direct chat if that answers the question or not, but I like the graph. The thing just goes down like this. So I'm responding to direct chat. The thing just goes down like the graph. I don't know exactly what that means. Each one is going up, and a graph, a cosine graph could describe, a separate cosine graph would be drawn to describe each one of these. Each one of these is described by an identical cosine graph, but the cosine graph, but the cosine graph starts in a different place for each one of these. Like for the very first one, the cosine graph actually starts. Maybe this is a good way of saying it. For the very first one, the cosine graph actually starts at 1 or at A on the y-axis. But then the next one, it's actually a sine graph. Like it starts at the origin. And then the next one, it starts all the way at -1. So it's cosine graphs, but they're each being shifted over by pi over 2. I don't know if that answers your question or not. Wait. Okay, this is a different question. I'm glad I'm getting questions about this. And honestly, please, it's really good that you're asking questions. The other class also had questions that wasn't exactly on this part, but this is super important. So I'm glad that people are asking questions. So someone else, and the first person who asked, I don't know if I've answered or not. You might still want to ask a follow-up or tell me. But now someone else in direct chat asked, so are they all the same distance away from each other? Yes, if I'm understanding your question, the answer is yes, if I'm understanding what you mean. I am absolutely saying that each one of these vertical oscillators is equidistant. Oh, they're all spread out equidistantly along an x-axis, yes. So the first oscillator is like at 0 centimeters. The next oscillator is like at 1 centimeter, let's say. The next oscillator is like at 2 centimeters. The next oscillator is at 3. So it's masses on springs, all being placed equidistantly Yes, all the same distance from each other along an x-axis. But then we let them all go in motion. I mean, we set them all in oscillation, so they start oscillating up and down. They're the same distance away from each other horizontally. What I'm also now saying with the pi/2 business is that they're the same distance away from each other. Each one is the same distance in terms of cycles from the next. Like each one is a quarter cycle away from its neighbors. So like oscillator number 1 is a quarter cycle behind oscillator number 0. And please, everybody hear this. This is the part that either will help or not, or will show you that you don't understand. I'm saying oscillator 1 is a quarter cycle away from oscillator number 0. Like, again, yes, it's equal spaced on the meter stick. Oscillator 0 is here. Oscillator 1 is 1 centimeter away. Oscillator 2 is 2 centimeters away from the original one. In terms of cycles, I'm saying sorry, the chat is in the way. Pardon me. I'm saying oscillator number 1 is a half cycle away from oscillator 0, meaning that when oscillator 0 has all the way up, oscillator 0 is all the way up to the equilibrium by the time oscillator 1 starts at amplitude, or vice versa. It doesn't matter which direction. So they're a half cycle separated from each other. When one is at amplitude, the other's at equilibrium. And then I'm saying same deal to oscillator 2. Oscillator 2 is a half cycle away from oscillator number 1. And oscillator 3 is a half cycle away from oscillator number 2. But what that means, that might be throwing some of you off. It used to throw me off. What that means, if each one is a half cycle away from the previous one, that means that like oscillator number 2 is 2 half cycles away from oscillator number 0, right? And oscillator number 3 is 3 half cycles away from oscillator 0. So oscillator 0, if you look at the first equation, has a phase constant of 0. The equation that describes oscillator 0 is just y number 0 equals a cosine omega t plus 0. But the equation that describes, say, oscillator number 2, y2, the equation that describes oscillator number 2 is is y2 equals a cosine omega t, like all the same facts as all the others, but plus 2 times pi/2. It's 2 quarter cycles away compared to 0, because it's 1 quarter cycle away from number 1, and number 1 is already 1 quarter cycle away from number 0. Wait, I'm going to pause for a second. Could one of the two people that just went in the chat, could you tell me whether I just made it better or worse for your understanding? Like, oh, yes. Oh, that's a great question. Okay. Yeah, okay. Yes, you do. Oh, yes, you do. You just proved it. Okay. So someone in the direct chat, this is so great. See, this feels like class to me. I don't know about you people, but it feels a little bit more like class this way. And these questions are great. And admitting you don't totally get it is so important. And the other class did. Okay, anyway. Yes, someone in the direct chat just said, wait, if there are many oscillators, would the numbers start repeating? Yes. Totally. Now, I mean, the answer is yes. And there are many oscillators. We are assuming there's many oscillators, and we are assuming the numbers start repeating. If by the numbers we mean like the value of y, yeah, totally, they'll start repeating. Yes, like the first one's at amplitude, the next one, especially if the phase constant is only like a quarter cycle, then it's only going to take like 4 oscillators until you've cycled back fully. So yes, like the first one's at amplitude, the next one's at equilibrium, the next one's at negative amplitude, the next one will be at equilibrium, the next one will be at amplitude again. They will so they'll be at staggered heights, but it'll start repeating, like even in this pattern on the page, like the very 4th oscillator is in the same place as the 0th oscillator, exactly what someone in the direct chat is saying. So yes. Okay, so hopefully a couple people maybe understand this. Now, all I'm trying to do right now is I'm saying if we made a bunch of oscillators that were all staggered in phase by a constant step, then we could capture this whole collection with one equation. And if that step happened to be pi over 2 radians per meter, then the one equation would look like this, would look like the one in the middle of the board. Now, right? So we could capture this whole thing with one equation. We have 15 minutes left. We could capture this whole thing with one equation. It's as general as possible, except here I'm assuming that phi, the phase constant, is pi over 2 times x, right? Like instead of just phi, it's just some number. Phi over phi is now a rule. It's now its own little function. Like to know the phi, to know the phase constant of any given oscillator, you actually have to plug into its own little equation here. You have to say, oh, well, how far out am I? What is the value of x? Oh, if x is 7, then I plug that in and I say, oh, phi is pi over 2 times 7, right? It's like a function within a function, so to speak. But once you do plug in, then you would know, once you plug in for x and once you plug in for t, you would know how high any given spring is. Like if someone walks in and sees this whole collection and says, hey, how high is a spring? You would say, well, you need to tell me 2 things. You need to tell me when are you looking and which spring are you looking at? Like, are you looking over here or are you looking over here? But if you tell me I'm looking at t equals the 14th second, and I'm looking over here at the 14th centimeter, the 14th oscillator, if you plug in a value for t and you plug in a value for x, then we have an equation that tells you exactly how high that spring is. So we've got one equation that captures this whole collection. The only catch is that this equation assumed the specific example of pi over 2. There's no reason that we always have to use pi over 2, or I'm just using it as an example here because it's easiest to picture. So the phase step, the number of radians that you increase the phase by per each meter that you walk along the x-axis, that number of radians per meter could be any value. It doesn't have to be pi over 2. So from here on in, I'm going to call that value k. What this here, you can't really read this. What this is a big letter K. Now I'm just cutting straight to that's a big letter K, but it's not the Hooke's law K. Unfortunately, it's a little confusing that we have K again. It's unfortunate, but it's just the way it is that we have K again. So I'm just saying not. Okay, I write them differently. The old K I just wrote as a K. This K I write with serifs on it. You can do whatever you want. You can make it lowercase, except unfortunately, you get another K later on that's also lowercase. So this is a different K. This K stands what I'm saying is now, this K is a measurement of radians per meter. If you were to make a little graph and think of how far out you go in meters, looking at this collection of oscillators, then the number of radians of the phase constant is directly proportional to the number of meters you're looking. It's a straight line function. Like when you look at the 0th meter, when you're looking at that 0th oscillator at the edge of the meter stick, it has a phase constant of 0, right? But then you go over 1 meter, the phase constant goes up by 1 times what? 1 times pi over 2, or whatever the number is. It goes up by 1 times that. Call that number K. If you think about it, K is the slope of the radians to meter graph, right? Like it's the amount. K is the amount by which you rise in radians for every amount of run that you look at in meters. K is the extra phase delay or head start in radians that you apply for every extra meter that you're walking along the x-axis. So K in general is the size of the phase step. Like again, we used the example of pi over 2 a minute ago, but it could be anything. Whatever it is, whatever K is measured in radians per meter, right? So if you look at the equation now, that means in general, we could capture this whole collection of phase staggered oscillators. We could capture this whole collection in one equation, one general equation that says y equals a cosine of omega t plus or minus k times x. This is okay. This is now okay. So the one equation, like okay. Okay, remember now, this is a subtle distinction. We started like months ago, whatever, saying one oscillator is like X or Y or whatever. Y equals a cosine. It could be any variable, remember. So let's say one oscillator was Y equals a cosine omega t. Then we realized this week, last week, that actually, if you want to be a bit more general about it, if you wanted to account for any kind of head start or delay, you could say that one oscillator was Y equals a cosine omega t plus phi, plus some number, right? This is what I just wrote at the way bottom of this is one oscillator. What I'm now saying with this one subtle change, if I change phi to k times x, if phi is no longer a number, but phi is a number times x. So remember, phi, the phase constant, was measured in radians. But if instead of that, I put in a little function, I put in k times x, where k is now measured in radians per meter, and x is measured in meters. So the meters cancel out, and the whole thing together makes radians, right? If I do that, now I have a collection of identical oscillators, all spread out evenly in space, but all staggered in phase by a constant step, by a constant amount of radians per meter. That constant amount is called K, right? K is measured in radians per meter and then multiplies by X so that you have radians, just like omega is in radians per second and then multiplies by the time, the seconds, so that it cancels out, the seconds cancel out and you're left with radians, right? K is to space as omega is to time. If we now write this equation with a kx instead of a phi, it makes all the difference in the world. We've now introduced a second independent variable, right? We now have a function of two variables. It's very different. If we just write y equals a cosine omega t plus phi, it might be a new symbol to us, but it was a constant. It's just a number. If we just write that, it's one oscillator. But if we write kx in there, we have a function of two independent variables, time and horizontal space. What we've now captured is a collection of identical oscillators staggered in phase by a constant step. And the reason this is also important, and the reason you probably recognize this equation from lab now, is this number K, this amount of radians per meter, this thing, you may know. The name for this K is just like omega was angular frequency, rate of cycles, number of cycles per unit time. This K is called, you know, from lab, but I'm sure it's always the most confusing thing when it's first introduced in lab. This K is called the angular wave number. The angular wave number, K, if omega was the number of cycles per unit time, K is the number of cycles per unit space. It's radians per meter. And it's called the angular wave number because if you step back and look at this whole picture that we just created, what we've created now, this is a wave pulse or a wave. This is a wave. We've got 3 minutes. Let me emphasize this now. I'm saying this is an oscillator, or even this is an oscillator. Something going back and forth harmonically, cosinusoidally in time is an oscillator. That is not a wave. It's a thingy thing. But if you arrange an oscillator next to an oscillator, next to an oscillator, next to an oscillator, if each one of these objects oscillates in time, but if their oscillations are all staggered deliberately, precisely in space, right? Then we have cosines in time. And if you look at this picture, if you look at this picture, each one of these is doing cosines in time, as you found out in lab 3. But yet, so for any given horizontal position we look at, we see a movie of that ultimately can be described by cosine oscillation in time. Y as a function of t, if you pick any constant x, is a cosine function. But if you pick any constant t, if you just look for one moment, and that's what this picture is, if you pick one moment in time and look at what y is doing as a function of x, if you picture one constant time and look at how the heights of these different springs are varying across the horizontal axis, then you see a cosine picture. And that's what you saw in lab 3. Lab 3 said hold x constant and you'll see y is a cosine function of t. Hold t constant and you'll see y is a cosine function of x. What you see here is crests and troughs propagating through horizontal space. When you arrange a bunch of harmonic oscillators and let their oscillations oscillate, if you arrange their time oscillations into a space oscillation, you get a wave. A wave is not an oscillator. A wave is oscillations in time and space at the same time, right? Harmonic oscillation is the fundamental ingredient of wave motion, a collection of phase staggered identical oscillators is a wave. That K is called the wave number for that reason. And this whole thing, and this is the last minute, I'm just going to say, this is now a wave. This is now an unthingy thing in that when you send a pulse from one lab partner to the other, shaking a string, right? And I know it's the last minute. This is the last thing I'm going to say. But if you send a bump, a crest, or a trough from you to your lab partner, you observe a bump in the string propagate in a certain amount of space horizontally in a certain amount of time. And you could write down the measurements and you could make a calculation of its velocity and you could predict how far it's going to get even farther in some greater amount of time. You see observable, calculatable, predictable motion of some kind of bump in this long metal coil, right? And the bump travels horizontally from you to your lab partner. And all that is doing any kind of traveling at all is metal. And yet there is no piece of metal that ever makes a journey from you to your lab partner. This is unthingy motion in that there is a motion and it is purely scientific, fully calculable, fully measurable, fully reproducible, fully predictable motion, but there is no particular thing enacting that motion. All that's moving is metal, and there's no metal that moves from one end of the horizontal space to the other. This is wave motion. This is unthingy thing. This is the point of the class, and this is composed of harmonic oscillations in time and space at the same time. It is pattern of patterned motions. That's what a wave pulse is. That's the point of this. Okay, we went over time by a minute. I apologize. I'll answer more questions on Wednesday. Great questions, though. Have a great day. I'll hang out for a second. Yes, have a good day. All right, have a good day. Thank you.
Bye, Professor. Thank you.
Bye. Thank you, guys. Thank you.
Have a good day.
Thank you. You too. Thank you.
Have a good day, Professor.
Have a good day. Thank you. You too. Awesome. That is a good question. Yes, I keep. Hold on. Can I ask? Good question. Oh wait, let me turn off the recording. Hold on one second.